So now I'll show you how to solve a differential equation for its equilibrium solutions and then classify those solutions according to their stability. And then I will also show you in that process how to construct the phase line. So for this differential equation, since it is autonomous, the equilibrium solutions actually will correspond to the zeros of this differential equation. So what we'll do is we'll take dy dx equal to y squared minus y minus 6, and we're going to be setting that equal to 0. So y squared minus y minus 6 can be factored into y plus 2 and y minus 3. See that? Minus 3 times positive 2 gives you negative 6. Minus 3 plus 2 gives you negative 1, so this works out. So from this you get y is equal to negative 2 and y is equal to positive 3. So now what we do is we turn to that phase line. And we want to put on that phase line negative 2 and 3. So then what we do is we look around these points and we determine what the sign is for the derivative around these points, these solutions, right? Negative 2 and 3 are both equilibrium solutions. It's just a question of, are they stable or unstable equilibrium solutions? So notice if I take some number less than negative 2, negative 3 for example, and we plug it in to the differential equation over here, it's easy to see that the first term would be negative and the second term would be negative, so a negative times a negative gives us a positive. So that means that the differential equation has a sign that is positive, so it's greater than 0. Between negative 2 and 3, it's pretty easy to see that you would want to take 0 as that test point. So then you'd see that dy dx, if you plug it in, will give you a negative value, which means it's less than 0, so the sign of it is negative. And then if you take something greater than 3, you will have positive yet again. So there you go, right? Now the question is, in constructing the phase line, what does it actually look like? So let me pick a different color here to draw the final phase line. So if I have negative 2 and 3, and we said less than negative 2, we have the derivative, the differential equation, is going to be greater than 0, which means the phase line will actually, we'll put an arrow going to the right. So you want to keep in mind if it is greater than 0, think positive, moving left to right. Between negative 2 and 3, that value is less than 0, so it's going to have an arrow that points to the left, going right to left. And then if we're greater than 3, we are again moving left to right. So in our phase diagram then, what I'll do is on these points, I will now replace those hash marks with what those solutions actually are. So in this case, this at negative 2 is a stable solution because those arrows are pointing inward towards negative 2. And at 3, they move away from it. So I'm going to put an open dot at 3. So there you have it. At negative 2, you have a stable equilibrium solution, and at 3, you have an unstable equilibrium solution.